Greetings, everybody. My name is Lazaros Moysis from the Physics Department of Aristotle University Thessaloniki here in Greece. And our topic today is a self-organized lattice diffusion model with vaccination policy, application to Greek COVID epidemiological data. So, first of all, we will discuss a little bit about this sort of self-organizing diffusion lattice models. We will talk about the phenomenon of critical slowing down. We will see how our proposed model can be used for COVID fitting, and then see what topics are worth studying next. So, first of all, what is a lattice model? A lattice actually consists of a discrete grid, and this grid consists of individual nodes or cells, as we say, and each one carries a specific charge. They are all connected to their adjacent cells, and inside this node, this system, when a cell becomes active, what they do is they exchange their charge with their adjacent cells following a specific deterministic or in some cases probabilistic rule. For example, in sand pile models, what we do is we set a sort of diffusion threshold, and if a charge in a specific cell goes above this threshold, what does it do? Its charge gets diffused into its adjacent cells. See, for example, if we set a diffusion threshold to 1, let's say this cell, for example, becomes active, what does it do? Its charge of 1 gets distributed on the top, bottom, left, and right cells. So we have plus 0.24, plus 0.25, plus 0.25, plus 0.25. Top, bottom, left, and right. And of course, the right one gets lost because it is on the edge of the grid, but we can change that. We can consider periodic edges, so no charge is lost. So once this becomes active, then the next cell becomes active, its charge goes to 1, it diffuses, then the next one becomes active, then the next one, and after some iterations, we see that no other cells remain active and the diffusion process stops. So this diffusion process, for example, depends a lot on initial density. So it may take just a couple of iterations for the model to diffuse, as we see right here. After just a couple of iterations, the model completely diffuses. While in other situations when the initial density is much higher, the model may take a lot of iterations to diffuse. So here for 55% initial density of active cells, the diffusion may take a really very high amount of iterations. So this phenomenon, we usually call it slowing down, refers to the fact that over a specific threshold of initial density, we may have an abrupt transition towards the amount of time it takes for the model to diffuse. See here the initial density, the amount of iterations, and the percentage of active cells, and you see that there is a very abrupt change where if we go above around 55% of initial density, the model takes a really long amount of iterations to diffuse. So this change here is very dramatic and it happens very abruptly. And of course, this is the case where we don't add charge at random in each iteration, but a similar phenomenon happens when we add additional charge in each iteration at random. We have this abrupt phenomenon, but over a lot of time, the model reaches this sort of balance where the charge lost and the charge gain sort of reaches a balancing point. Again, this is called self-organizing criticality. Now, why are such models useful? These self-organizing systems are extremely useful because they can be used to model epidemics, for example, COVID or measles, other types of diseases like HIVs, or even forest fires. So they are very useful, although very simplistic, in modeling real-life phenomena. And more importantly, the phenomenon of critical slowing down is something that appears in many real-life phenomena. And it's sort of a warning signal for imminent outbursts of phenomena like COVID cases, COVID surges, or epileptic seizures in some cases. So, you know, by considering these models and even more complex ones, we may actually manage to estimate and, you know, be able to detect realistically early warning signals. So in some of the recent works, Professor Stavronidis and other colleagues considered, for example, fitting some lattice models into real-life COVID cases. For example, here in France, you see a very nice fit of the epidemic. And also in other simulations, they also managed to not only fit the model to a specific case in a city or in a country, but they also managed to estimate how close the country was into this abrupt transition. So motivated by this, actually, we try to consider a model that is slightly more complex. The idea is to model a vaccinated population inside a lattice. So our idea is to have two different actions in a lattice. So we categorize each cell into vaccinated and unvaccinated. The unvaccinated ones, they behave exactly like we showed, but the vaccinated ones have some difference. The vaccinated ones have a much higher threshold for diffusion. So the threshold for a vaccinated cell is actually much higher. And moreover, when they cross this threshold and diffuse, they diffuse a much less amount of their charge. So we assume here that some amount of charge is lost. And the idea here is that vaccinated cells are much more resistant and they are much less able to transmit the virus themselves. So the goal here is to probably manage to model the epidemic spread over the last couple of years, where we have also a steadily progressing vaccination of the population. So in our proposed model, we considered a periodic lattice. So the only way charge is lost is through vaccination. We have some active cells that we initialize based on the active cases, in the population. The inactive cells are not zero because this helps modeling the results much better. And we have an added charge which happens at random, and also a vaccination which appears at random, and it is randomly distributed throughout the graph. And the goal here is to manage and fit to real-life data, possibly obtain oscillations in the activity. So the overall amount of degrees of freedom are actually just two of them. It's the amount of charge that we add in each iteration and the amount of vaccination in each iteration. So we practically have 2 degrees of freedom. And another couple of parameters is the simulation time and the charge that the inactive cells have. So for this model, of course, there are many cases that we can consider, many waves here in Greece and, of course, in other countries as well. So, for example, in one of these waves that you see pointed right here, after some fitting, we see that we can relatively fit satisfyingly well. Actually, our goal here is to manage and model the first part, which is the peak, and manage the fade out, which is the tail. And of course, we're trying to do this for different time waves. Here, some issues are, for example, how many iterations we should consider, but we usually have them being time varying. The result you see here is an average of 50 simulations where you see with dashed lines the best and worst cases. So the mean value goes relatively well in this wave, although in other waves. So for example, one more point here is that by changing the amount of vaccination, you see that we have with a lower vaccination we go to a much higher overshoot, or with the higher vaccination we manage to have a much lower overshoot in the time series. Which is sort of a projection of what could be better, in a realistic setting. Of course, in other waves, the results may not be equally satisfying. For example, here in this wave where we have a very wide plateau, this is much more difficult to achieve for this sort of system. But I believe after some trial and error, we will manage to achieve this as well. So we're at a very good point right now. We're trying to fit it towards different parts of the epidemic here in Greece. I think we will overall have very positive results. So conclusions, what we did overall is propose a different model of lattice sample spread, where we have two different policies. We have this sort of addition of a charge, and we have a vaccination policy that changes the way the cells behave. So this offers actually an additional degree of freedom that we believe can make the lattice more adaptable for modeling applications. And of course, now we aim to expand this towards many different directions. First of all, at the moment, we're trying to fit towards many more waves in Greece, but we're also trying to consider different types of lattices, for example, small world networks or non-uniform networks or cellular automata. So the idea behind small world lattices is that we can model some super spreader cells that can interact with many more than just 4 of the adjacent neighbors. So cells that behave like that or maybe like that. And this is very indicative of people that travel a lot, for example, and they come in contact with many, many more colleagues. So this is sort of an idea that we believe can give you a better fitting in the model. And another one is, of course, to consider a non-uniform lattice. As we see right here, we have overfitted Greece, for example, in the lattice. Some areas, some cities are much more dense in population. So this could be a much more complex model that would be a bit more realistic. And finally, what we're trying to do is a bit more big project, but we're trying to use cellular automata. In cellular automata, they are a bit different than Sunpine models because here we have each cell being in a different state during the simulation period. So a cell can go from susceptible to infected to being symptomatic or asymptomatic or recovered, and they interact with a much wider region than just their adjacent cells. So we have different categories of cells. It is a much more complex system, but we believe it has a lot of potential. Already there have been some work that they managed to estimate, for example, the effect of intensive care units, the effect of lockdowns, and the results are very promising. And we believe we can extend the existing models by considering vaccination levels, vaccination cells, as we showed in our own model, maybe an age structure population, maybe different viral strains. So, for the existing models, again, there are a lot of ideas that we can use and extend towards future studies. So overall, we're at a very good direction, much more simulations to perform, but overall, I can say the results are pretty positive, and I believe we can consider a much more simplistic, but a bit more complex model with some additional degrees of freedom to use our simulation basis for COVID fitting. So, thank you very much for your attention. I will see you in the Q&A section. Thank you very much.